number 2, simple harmonic motion. So firstly, define simple harmonic motion. How would we define simple harmonic motion? I mean, we know what it is, but what's the definition of it? Yeah, there's many ways to think about it, but the simplest way to define simple harmonic motion, simple harmonic motion of a mass m is where the mass m is subject to a force proportional to its displacement, its distance. I.e., simple harmonic motion is when the force is proportional to its position, or in other words, F equals K times X. And by the way, what's the name of this law? Hooke's law. That should cover it. That's K.
In the exam, can we just put the formula and define the terms?
You can write the formula down, but you really need to have a sentence too for full marks for the definition. Is that okay? Right, now draw a graph to show how the total energy, kinetic energy and potential energy of a mass moving with simple harmonic motion varies with displacement. So it's not entirely clear what he wants on the y-axis, but it sounds like it's the position. But I wouldn't be entirely convinced of that. So basically he wants you to talk about the steps in simple harmonic motion. A2. Oh, how many marks for this now? 3. So 3? Okay. So this axis is the time. Did you just nearly fall backwards?
No, just not.
It's funny, but it's true actually. Right. So what happens? Well, you would have something like this, okay? Imagine like a spring. And you pull it back. And then what happens? You release and it moves simple harmonic motion. So it goes like this. If you imagine it going up and down. Okay? Now he wants you to talk about what happens just before and just after the equilibrium. And I think what he means by equilibrium here is the place here at 0, the center, so to speak. So let's look at just before. So here we'll call this the equilibrium. So just before in red, it's going up or down. It's going down. In fact, just after, it's still going down as well. But in black here, what direction is the force? Well, here the force is pulling it to the center. But the direction here, the force is up because it's slowing down. What else is happening? The velocity. Is it getting faster or slower here? It's getting faster. And here, slower, yeah. So what's happening to the kinetic energy? I'm running out of space. It's increasing. And here, decreasing. Now remember, the total energy must be balanced. So if the kinetic energy is increasing, what's happening to the potential energy? And here? So there's a lot of stuff here, but you then have to write a sentence. Before equilibrium, the kinetic energy increases, therefore potential energy decreases. What else happens? the force acts towards equilibrium, in this case, down. Anything else I said in the graph? Yeah. Oh, and I should also say the total energy is constant, of course. And then you have to say the same thing, but then on the other side, etc., etc.
When the spring goes down, when the reaction
When it's going down, it's because the spring is pulling it down. That's all.
when it reaches, it stops.
When it reaches, it stop. No, it doesn't stop. It goes, it gets faster and faster, and then it starts to get slower and slower again. No, to be careful is, let's not think about reaction here, because it's not really a reaction, you know. It's the force is pulling it down, and the further it goes down, the force decreases. At the center, at equilibrium, there's no force. And then when it passes the equilibrium, the force gets bigger again, but in the other direction. Yeah? Is that okay? All right.
This simple harmonic motion, can we do the graph of the pendulum?
Is that in it?
It's a simple harmonic motion. We just say of the mass moving with simple harmonic motion. So can we use the pendulum graph?
Well, yeah, but what do you mean the pendulum graph? It'd look the same. No, you're thinking of that's what the formula, isn't it? The t-squared formula. Yeah. Right. A clock is regulated by a simple pendulum that has a time period of 2 seconds and an amplitude of 4 centimeters. Determine the length of the pendulum. All right, not so bad. What's the formula here? T equals 2 pi root L over G. Now, what does he want? He wants the L. And what does he give you? He gives you the T, doesn't he? It seems easy enough. So what's the T here? 2 seconds, is it? 2 equals 2 pi root L over 9.8. 1. Cancel, cancel. Bit of rearranging. 9.81 over pi squared. That's the L, which actually is roughly 1 meter. Can you tell me what it is exactly? So it should be like 0.95, 96 maybe?
0.99.
Oh, bigger than I thought. 99, what's after the 99?
That should be 2.9.
Okay. Easy peasy. Easy peasy. Right, what is the maximum velocity of the pendulum? So I'll help you out here with this one. Look here, please. The pendulum, he wants the maximum velocity. Okay. Now, he gives you the amplitude. What does he say it is? 0.04 meters. So remember I said when the pendulum is swinging, it's kind of heading along an arc, isn't it? But we said to make our life easier, you can say it's roughly heading on a straight line here. Okay? The amplitude in simple harmonic motion is how far out it travels from the center. So in this case, what is it? 0.04. So that's pretty much telling you how much it swings. Okay? Now, I have a feeling in the marking scheme they're not going to do it this way, but that's okay. Yeah, I think they're going to, well, I'm going to use kinetic and potential energy, but I think they might use more of the simple harmonic motion formulas. But I would like to use a little bit of trigonometry. So at the beginning, the pendulum is like this, isn't it? And then at the end, or at the center, it's like this. It swings down. Yeah? So here, how big is this piece here, roughly? 0.02, did he say, or did he say 4? I think he said 4, yeah. How big is this piece? 0.99. So somebody please tell me what the height here is using Pythagoras. So 9.8 really. 9.7.
8.5.
So 8. So 9. If you round it up, meters. Now, does it have kinetic energy when you pull it all the way back? No. What does it have? Potential energy. And what's the formula for potential energy? So what's the M here? Does he give it? No. Oh well, we can cancel it out in the formula, so it's okay. M G H. So can you just multiply, please, the these two numbers? 9.6 M. Now here, does it have potential? No, because it's all the way down. What does it have? Kinetic. And what is the kinetic here? A half V squared. And that's what he wants, is the V. So the kinetic at the end here has to equal the potential at the start. So therefore this must equal a half mv squared. So it actually doesn't matter that he doesn't give us the m, because what happens here? They cancel. So therefore v equals 2 times 9.6 square root. What's that? What is it? 19.4? Oh, what is it? Yeah. That one is okay. I think what would catch people out here is first you have to figure out the height, and you need to use a little bit of trigonometry, like just Pythagoras theorem. Okay. Right. That is part 2. The next one is a 1-mark question, so it's just something you should get instantly. At which position in the motion will maximum velocity occur? Now that's really interesting. Hey. Listen, Chris. I suspect in the marking scheme they did A part 2 a different way, perhaps just using formulas. But the way I did it means I already know the answer to part 3. Where must the pendulum be for maximum velocity? Okay, I guess I didn't actually need to know that to do part 2. But anyways, it doesn't matter. We know the maximum velocity happens where? In the middle, or in other words, at the lowest point. That's when the velocity is maximum. So the answer for part 3? At which position? At the lowest point. Okay, there's only 1 mark.
You can't say when it's reached the amplitude.
No, that wouldn't be clear enough. I know what you mean when you say that, but in the exam I don't think it'll be clear enough. Alright. Determine the maximum acceleration of the free end of the pendulum. So in other words, when is the acceleration maximum? At the top, yeah. At the top. Now, can you get out your formula books? Because in fact, I think there's also there's a formula for this in the formula book. So let's try and look at the formula book now. I think you have in your formula book, maybe you have this one, that the maximum acceleration, or maybe just acceleration equals omega squared a. Is that in your book? Is that in your book? It's not there? Well, it might be in the new book. Does anyone have the other exam I gave you? Do you have it, sorry?
What is the maximum?
Can I see what they do have in this exam, please? Ah, it is there.
That's 8.
Oh no, it's not. It's a little bit different, yeah.
I have the open.
Why?
No, it is.
Like minus one.
Yeah, here it is here. They write it a bit differently.
A equal minus 2 pi f
Yeah.
squared.
Yeah, we'll use that one. We could use this one too.
Page?
Page 3. It's kind of hidden. Now, he says, yeah, he says the acceleration equals minus, but I don't care about the minus, I just want the number. 2 pi frequency squared times position. So if you want the maximum acceleration, you should use the maximum position. And what's the maximum position here? The amplitude, the A. Now, I don't want to use the F because I don't know the F, but what do I know? I know the T, don't I? What's the definition of T? T is 1 over F, and F is 1 over T. So I can say that this is 2 pi over T squared times A, which will equal, what is 2 pi over T? This is equal to 6.28. What's the T? Is 4, isn't it? Or 2? It's 2 squared, and then it's 0.04. What's that now? 0.395 then, yeah? Okay. Oh my goodness, same thing really again. Which position will the maximum acceleration happen at? Yeah, at the top. At the highest point. You really want to use amplitude today. At the highest point. Keep it simple. Have you learned this expression yet? You know this rule? Some of us have seen this before. Keep it simple. Stupid. Have you ever heard this rule before? No? My physics and maths teacher taught me this. Now I'm teaching you it. Okay? So keep it simple. You don't need to put this extra one in at the end, but most people do. Because, you know. Right. C now. A mass of 300 grams is hung from the end of a long spiral spring and causes the spring to extend by 15 centimeters. The mass is pulled down a further 10 centimeters and released so that it oscillates in a vertical direction with simple harmonic motion. So I'll draw this. It's a little bit tricky, okay? So please focus with this one. You have a spring, and he says it is a 300 gram weight here, and it causes it to extend by 0.15. Okay. Delta x equals 0.15. Okay? Now, when he does this, nothing happens. It doesn't move. Why do you think it doesn't move? Like, why does it just hang here? Well, the reason being that the downward force, what's that? mg equals what? The upward force. Now, what is the name of the downward force here? It's just the weight. So, like you said, it's mg. So that force will equal 0.3 times 9.81, which is what, please? 2.943 newtons. Now, there's an upward force. What's the upward force? Well, no, what's the name of it? It's the force in a spring. Hooke's law, Hooke's force, you know. The spring force, yeah. So what's the formula for that? F equals K delta X, to be a bit more precise. It's the extended value. Now, what's the delta X here? Now, because these are balanced, what should it equal? Yeah, so with this I can find the K. So I have K times 0.15 must equal 2.94. So tell me what the K is then.
19.6.
Sorry, what is it?
19.6.
K equals 19.6. Now that doesn't answer the question, but it gets it started.
What
Yeah.
is the K?
Like the constant of the spring, like the stiffness constant. Now, what happens is it's pulled down a further 10 meters and begins to oscillate. So let's draw that diagram there. So here is your spring. It's pulled down a further 10 centimeters and starts to oscillate. So what does it do? Well, it goes up and down and up and down and up and down like this. What's the K for the spring? 19.6. Now, because it's oscillating with simple harmonic motion, what's the A here? Could anybody know what it is? In fact, that's 0.10. Because if you think about it, he pulls it down 10 and then lets go. So the 10 is the amplitude. Now I have the A, now I have the K. And I think there is a formula that has the K and the A in it if you want to look at your formula book. It is, does he give us the mass too? What's the mass?
T equals
300, oh yeah, of course, yeah, 300 grams. So, that's great. You also have the mass now. The mass is 0.300. So if you look at the bottom of page 3, you can use this formula.
T equals
Yeah, T equals 2 pi root m over k. And what does he want? The T. So 2 pi root 0.300 over 19.6. Okay, please tell me what that is.
Are those zeros?
0.300, yeah, sorry.
777.
0 point lucky sevens, is it? 777? 778.
No. 7.
Oh, 777, exactly. Nice. You all have casinos in your home country, right? Well, maybe not in Saudi, actually. No casinos? No, okay. You know that game where you pull the lever? If you get 3 sevens, then you get the jackpot.
Yeah.
You know this one?
Yeah.
Okay. What's next now?
Determine the position of the mass.
Yes, where is the mass after 2 seconds it's released? So we need a formula here. Do you see the formula called displacement? Do you see that one there?
Yes.
Now, I think the symbol here is a little bit confusing. He says, which number is this? Part 2. He says displacement equals x0 sine 2 pi ft. And in fact, the x0 here, and I don't know why they use x0, and maybe in the new version they use a different letter. Do you remember one of the formulas? What was it? Young's double modulus. One of the letters is wrong. Yeah, I don't think there should be x0 here. It should be A, amplitude. Okay, so I'm going to change it here for you. And write that in on your formula book if you have it here. It should be A. Now, there's a further complication too. He only lists one of the formulas here, but there's actually 2. And the other one is this one. And you might say, which one do I pick? And does anybody know? Do you use the sine or do you use the cosine?
Depends on where you
Very good. It depends on where it is at the beginning. So which is which, do you think?
sign for the sign for cos. I mean like cos will leave it for the
Sine. Because it's up.
Yeah. From the right.
Good. We're thinking now. We're thinking. So it's like this. You have the pendulum and you pull it down, okay, and then you let go, and what happens? It goes up. But don't think about up or down. Think about bigger or smaller. So if I pull it down and let go, does the spring get bigger or does it get smaller?
It's smaller.
Smaller. Gets smaller. Because if I pull it down and let go, it starts to shrink. So this is how you distinguish between the two. If it gets smaller, which do you think you use?
Cosine.
Very good. The cos, because cos gets smaller. And if it gets bigger, the sine. Now, how would it get bigger? That's if you have a spring and then you flick it. You know, you go like this, you flick it. So if you had a spring here, like imagine it's just lying here on the table, like this way. And if I come along and just go flick, it gets pulled down and goes like that. Not so common. It's probably more likely to be cos. Anyways, let's plug in the values. I don't want to use my f, so what will I use instead of f? 1 over t. Okay, so let's fill in the information. What's the big A here? What does he say?
0.1.
0.1. And what's the big T? Did we get that? Did we calculate the big T? I don't remember.
Yeah.
No, no, we didn't.
No.
Go back.
No, that's the small t is 2 seconds. The big T is the period. I don't think we calculated that, did we? This one?
No.
Oh, sorry, we did. Yeah, sorry. What was it? Do you remember? Oh, yeah, the lucky sevens. 2 pi over 0.777 and the small t? 2. Please make sure your calculator's in radian mode. Tell me what you get.
Minus 0.029.
Are you sure?
Is it inverse? Or
Minus is okay. No inverse.
So minus 0.0.
Okay. Minus 0. What is it?
0.89.